Good morning. Today, the paper we are looking at introduces NeRF, representing scenes as neural radiance fields for view synthesis. It is written by Ben Mildenhall, Pratul Srinivasan, Matthew Tanchik, Jonathan Barron, Ravi Ramamurthy, and Ren Eng. The basic idea is that we have a bunch of pictures of objects from different sides, and we have to come up with a system that generates the picture as if the object was viewed from any direction. So something like this. Specifically, look at the ship for example. We can see the changes on the water surface when viewed from a very particular angle. Or look at the drum kit. This is not at all a trivial task. There are many complicated details here. Here we can see some real world scenes. So this isn't some abstract thing, and we can actually use this in the real world. So that's ultimately the goal, to input a few pictures and be able to synthesize any kind of view using NeRF. As you can see, the task is called view synthesis. What we can do with synthesis, particularly in this paper, is that it takes into account also the viewing direction, which gives a much more realistic impression. But in order to really show you this, on the left you are going to see this novel view that is rendered, and on the right it's sort of like a fake thing that you couldn't do in reality. What we are going to do is we are going to keep the camera at the same position, but we are going to tell the scene that the camera is at like switching around, and that makes you able to see just how different a pic like a room can look if viewed from different directions. So the right one is really kind of physically impossible. It's just meant to show you how different things look differently if they think they are viewed from a different direction. So the same thing can be seen here. What you get automatically out of the systems are depth maps. These are notoriously hard to get, especially for complex scenes such as these, and it handles it fairly well. You can even do something like AR right here, since you now have a representation that tells you how far everything is away, and you have it from different views, as you can see. You can even get meshes, so I should be able to move that around here. This is now a mesh. It's not only view synthesis, but you can actually fill out the voxels, which is a slightly different task. And if you have pictures from all around, you can synthesize kind of any view in between, as you can see right here.
Now that we have gone through what this method is capable of producing, let's go over how it actually works. It uses the idea of neural networks and deep learning, but not in the way we might use it traditionally. The abstract of the paper states, and this is stated on the screen right now, is that the method achieves state of the art results for synthesizing novel views of complex scenes by optimizing an underlying continuous volumetric scene function using a sparse set of input views. Now the problem is that in research papers they tend to use very concise wordings, but in the end, what ends up happening is that it becomes really tough to understand what they're actually trying to convey. So this one sentence that I have spoken right now, this actually conveys the entire essence of what the model does. So let us break down the sentence in part and try understanding it at our own pace. It states that the task of the model is synthesize novel views of complex scenes. That is views of the object at hand from different viewing direction and spatial locations of which we have no images. So what does this mean? This means, for example, you have taken an image of an flower. You have taken it from the position of your camera was at a specific location, right? Like some XYZ coordinate from the object. So imagine, and it has a different viewing angles. Like you might have tilted your camera to the left, to the right, up or down, different viewing directions you might have. So what this model is trying to do, imagine instead you wanted to see how the same flower would have looked at from a different position and from a different angle. So the task of this model is to recreate that. Now we don't have image for this data, right? But it is trying to artificially create it. It does this with a sparse set of images. That is few images in the data sets which it takes as input. It might take as input 30 images of the flower that we have stated from different angles, and it is able to recreate that scene digitally. Uh, and it creates a model by optimizing an underlying continuous volumetric scene function. So what is this last thing? We'll go over this later on, and we'll understand what it actually means. Now, I had mentioned earlier that this differs from the regular approach to deep learning. So how is it different to that? So we'll go over a traditional neural network. So in the traditional approach, we would have a data set of say 30 images of the same tree from different angles. Or maybe we have 30 images of a car, building, bike, etc. Whatever you need to have. Okay. Now we have this as an input, and we also have the target, like what we are trying to recreate. The target in this case would be the 3D models of the tree or the car or the building or the bike or the thing you're trying to create. Now we have this deep neural network, and we would train a neural network with this data set and expect as output a model of the object we give it to predict. So for example, we gave it different models for tree, building, bike, right? And then we might give it as input image a computer, and as output we would get a 3D model of the computer. Now this is the traditionally how you would have approached it. But in NeRF, we train a neural network only on one object. That is the object we want a model of. So, for example, if we want a model of a tree, we would only train it for that particular tree. Now, what this is actually overfitting, and which is a problem which usually always avoided in machine learning. But by this approach, instead of getting a 3D model as an output, the neural network itself becomes the model. What this does is it helps save ton of data. Like the previous approach that I had stated, that would output a 10 GB file to store the 3D model in the form of voxels. But with this new approach, you can essentially reduce the size of models to just 5 MB. From 10 GB, we are able to reduce it to the size of 5 MB, which actually happens to be smaller than the size of the images that you give it essentially. So, what do we have on the screen right now? I have been explaining how NeRF is different from traditional neural network, but I have not gone over what this actually means. So, let us go over it. We shall talk about what is the input of the model. So, it gets two things as the input. Now, I know it says five things: x, y, z, theta, and phi, but I'll tell you how it is two. One of it is the position from which the object is to be observed. That is the XYZ coordinates. So the distance from the object from which you want to view it, that you have to give in. And as I had said earlier, we have to tell it the viewing angle. That is essentially the angle from which the object is being observed. The angle is in two parts. Here it's written as theta and phi. Thus, we have a 5D coordinate system, three from XYZ and two from viewing angles. Now, if you remember, I had stated that it produces novel views of complex scenes by optimizing an underlying continuous volumetric scene function. So I had said we'll go over this continuous volumetric scene function, right? So this is that continuous volumetric scene function. It is the XYZ, the theta, and the phi. Now, what does it output? In the middle, we have the model, and as outputs, we have RGB and theta. So the RGB is, if you know, red, green, blue. That is the color at that particular position. And theta, my bad, I said theta. Sigma is the density. That is there even anything there in the first place at that particular location? Okay, so you can see if we want to view an object from different angles, these are the different perspectives. So as you can see, let us say we pick this particular viewing angle for that object. All right. And now we want to look at how it would look at that particular pixel, how the image would be. So what we do is we send a ray of light. All right. And then you can see these different blobs. So what do we do at these different blobs? We calculate the color and the density at all the different positions. So as we had said, the model is capable of outputting the color and the density. We would do that along the ray for all the different positions in the ray. Now this is the function that I had gone over earlier. So after calculating for all the different positions, what we do is we integrate it all together and we combine them so that we get the value or at that particular pixel. Now we have the value for that pixel. Now we can do it for the entire image, and we can do it for all the different possible viewing angles or camera positions, and voila, we have a 3D model. Okay, so if you have any idea of how learning works usually, the 5D model that was mentioned here, this is differentiable, and thus we are able to calculate the different values for the parameters. Thank you so much for listening, and I hope you now have an idea of how NeRF actually works.